let's get going. Welcome everyone to another edition of the MFEM HPC tutorial. We've been doing this for 4 years now. That's several times. And it's a chance for you to play with MFEM in an AWS instance in the cloud. It will be all in the browser. You can edit the files, you can build executables, run them, and visualize the results on the cloud, on your laptop, on your phone, on your tablets. The way this is going to work is first make sure you're on Slack. And the first thing you're going to do, which will take a while, is hopefully you can see my Slack here. You'll go into the MFEM tutorial channel and go / and run this command called request AWS. And you can see in the description here, this starts the MFEM tutorial app. So just like that. Just like this. Okay, when you do that, this takes a while. I already done it, so I get this message, but when you're successful, you will get a message like this, which welcomes you to the tutorial, and it gives you your own IP. Please do not use my IP. This is my own private little computer in the cloud. You will get your own. So what is MFEM? MFEM is an open source finite element library to perform simulations on high performance computers, supercomputers, child finite elements, MPI parallelism, GPUs. Our webpage is mfem.org. That's the place to go and learn about the project. We have quite a bit of information there. If you want to go to the actual code, that's on GitHub. You just follow this link. It's github.com/mfem/mfem. And this is where you get the latest and the greatest. Today, you won't need to do any of that. You're just going to get an instance in the cloud, your own little computer that will have MFEM pre-installed and our visualization tool pre-installed, and you can just use it. A lot of us are here in Portland State, and that's because starting tomorrow, we have our annual MFEM user meeting, the community workshop. That will be tomorrow, and the day after tomorrow, hosted here, Professor Posner. And we are actually in a conference room for those folks that are online with several students and other members of the MFEM team here that are going to also do the tutorial and jump in to help. If you have questions at any point, please paste them in the MFEM tutorial channel. We are kind of set up to answer them in parallel. If you are new to MFEM, one place to start is to go through the features and where we highlight things like how the finite elements, flexibility, the parallel scalability and GPU readiness, solvers we have, and the extensive list of examples. If you're ready to get going, the best place to start is the example codes, because they are documented, simple demonstrations of what different types of PDEs that you can discretize with MFEM, from things like diffusion to elasticity, electromagnetics, and so on. We have quite a long list of those. I think we are over 40 at this point. We're exactly at 40. Let's see who is going to do 41. And then there are also mini apps that are a little bit more advanced. There's documentation, getting started, articles, and then there are kind of a little bit more theoretical or more detailed things about finite elements, including some recommendations, books. There's also some images of things you can do in MFEM. And as part of the community workshop, we run this visualization contest, and the submissions there are always super cool. This is one of the winners. and there are many others here. This is another one of the winners. So if you're curious about cool simulations like this, the results from this year's visualization contest will be announced on Thursday morning in the workshop. This is the page for the tutorial. You can also get it from community tutorial. And this tutorial is designed to be self-paced. It's basically you go, hopefully there is enough information here that you can go do it by yourself. In fact, today we're doing it in the cloud, but you can download the Docker image and do it on your own computer, your own time. You can also just read the material. There's a set of HTML pages with some explanations. You have a local installation of MFEM. If what we do today is interesting and you want to put it on your laptop so you don't depend on the cloud, you could also do that and just follow the examples. Now, it's 6 pages, and this is the dependence. The first thing we're going to do is going to getting started. Then you need to go to the final element basics. Then you have a choice. And then at the end, some more details about what's in each lesson. And in the beginning here, we kind of give you an estimate of how long it will take and what it is. Okay, so if you were successful in getting an instance, you have these 2 links actually that you can click on. And I will help you set things up and go with you for this getting started. Then I will show you some of the other pages. But after that, it's really up to you guys. You start exploring on your own and just jump in to ask us questions. Okay, so the first thing we're going to do is set up the editor and the kind of developer environment. Here we say that you are getting an IP. Conveniently, this is already incorporated in this link. So the one that starts on port 3000. So if you click it, you will get an image like this. Actually, yours may say maybe a little bit different. You need to click on, I forget what it was called, Markdown here. But after you do that, you will get a browser like this. Okay, and it just follow the instructions here. You say open, open file or folder. Yours may be a little bit different because I already done that. Yeah, yours will look different than mine. Okay, so open folder, then you say MFEM, just like here. Then in the left pane, go to examples and select example 1 CP. I've already done that. So you should see something like this. And then we want the terminal. So you can get the terminal from here, new terminal. And you should have an image that looks like this, which is pretty close to what I got. Okay, so this is now a Visual Studio Code. This is just like the Visual Studio Code that you're used to, but now it's running in the browser window. You can edit files, and you have a terminal where you can build files and run commands. Okay, we need another window to open, another way for the visualization. It's at port 8000 and has this live extension. Again, in Slack, you should have this ready to go as a link. I just clicked on it. I'll pull this window. Put it here in the corner. Sorry. Put it in the corner and make it a little bit small. Okay. And when you move in this window, in the upper left corner will appear a link that says connect to socket. Click on it. So you connect, and then you click outside of it. So now, put things next to each other. I usually like to put them like this. You have the development environment on the left, your visualization on the right. You should get something like this. And just to test things out, go into the example directory and run example 1. And the first time you run things will take a while, but after that things are going to get faster. And the image here should automatically change to this image. And you should see about 111 iterations here. If you scroll up, you will see that we're solving a linear system with 21,000 degrees of freedom. They're running on the CPU. There's additional details. Order 1 is the first example. And if you want, you can click in the visualization window and use your mouse to adjust things. So let me pause here. This is the point where we want to get everyone to be at. And we'll continue. Please ask questions if you are not at this point yet. All right, well, this is your environment. And we're gonna use that, you're going to use that to learn more about MFEM. So go back to the tutorial page and look at this page, the next page in sequence, which is about finite elements. And this gives you just the basics of how the finite element method works. How is that translated in software in MFEM? And tells you about the internals of example 1 in more detail and allows you to run more examples and experiment and understand things better. For some of you, this will be old news. For some of you, maybe this is new. So if you're not familiar with finite elements and using them to discretize PDEs, go for this description that shows how finite elements work on the simplest possible problem, the Poisson equation, which is this PDE. Finite elements are linear combinations of basis functions like this one that allow us to discretize on really complicated grids, including grids curved with adaptive mesh refinement like this. And they use the so-called liberational formulation where you test the equation with a test function, integrate by parts, and you get this weak form where A is called the stiffness matrix, involve this inner products of basis functions, the gradients of the basis functions. B is the right-hand side, the log vector involves inner product of right-hand side of the PDE versus a basis function, and X is the coefficient of the degrees of freedom, the coefficients in front of the base function. So this is kind of in a nutshell. Of course, this is not a substitution for classes in finite elements or for the books. You can learn more there. But we put it here because we want to then connect it to what happens with example 1. Example 1 is what you have open here. You can just go and look at it yourself. It's about 200, less than 300 lines of code. And in this section, we go step by step and trying to relate each of the concepts about, for example, B, this linear form, is this right-hand side vector here that corresponds to this linear form, and A, B, and X, the stiffness matrix, the right-hand side, the vector of that corresponds to the right-hand side in a linear system, and X is the degrees of freedom. So you can go for these two sections at the pace. And this is in serial. I mentioned MFEM works in parallel. The parallel example is called example 1P. There's this we're adding P when we're switching from serial to parallel. So it's this code here. And in the next section, we go for the differences between serial and parallel. So there's very few things you need to change in MFEM to make a code that just simple and serial that runs on your laptop to turn it into something that scales. And it's mostly adding par in front of the classes. So very quick overview of finite elements, example one, it's parallel version. And then we have then we start adding these kind of sections where you can try things yourself. And when you see these green boxes, those are things that you directly can copy and paste. For example, this one, I just copied it. And you can paste them here in your terminal. Press enter. And when you do, you will see a new solution appeared here. -m means use this mesh, and the mesh from the data directory is called L shape. Unsurprising. This looks like an L. You can also run with the same example on meshes that are three-dimensional. So this is an example of three-dimensional problem, and I'll just show you the mesh here real quick and show you what the solution looks like inside. So you start with a maximum in the middle, and then you kind of go to zero. These are the boundary conditions in the boundary of the domain. Okay, one thing is we have these dot slashes here because in this VS Code instance, the current directory is not in the path, so you need to add that when you're referring to binaries in the current directory. And so far, the examples I showed were serial, but let's try something in parallel. It's MPI run. And we get an error when we run with MPI run. And that's because we're trying to run on 16 cores here. The instance you got, while cool, you will see in a second, anyone who has GPUs does not have 16 tasks. This is where this warning comes in here. You just use this dash oversubscribe, and we're going to overload the cores. So go and do it again. And now we actually run in parallel on 16 different pieces of the mesh, and we solve the same global problem. Okay. And this says that if you press some magic keys, you should be able to get this image here. Let's see if we can do that. Capital R, J, E, G, F11, and P a number of times. It's not this one. Stop me when I get it. Did I miss it? Sorry. This is not what? What is going on here? This is not the right one though. And also I will press A here. There's a secret key though. Here we go. All right, perfect. Now we're going to this. The end of this file is about this visualization tool that we called ULIS. All this magic will make well, maybe will make or will not make more sense. But for now, let me go back and maybe I should have mentioned all these pieces that you see here are the 16 pieces on which we solved. And each of these, I will have to zoom in quite a bit, is the computational mesh on each of them. So 16 MPI ranks, 16 parallel tasks, worked on each of these pieces independently. But of course, at the end of the day, we want to solve a problem that is a fully coupled, continuous problem on the full domain. And as you can see, the solution is continuous. And if you didn't know, you wouldn't recognize the boundaries between the subdomains. In this case, we're running on 16 ranks. MFEM can scale to hundreds of thousands of ranks, to millions of ranks. All right. Another cool thing here is that with this instance, we have GPUs. They're not the most powerful GPUs in the world, but they are GPUs, and you can use the GPU kernels in MFEM and run in the cloud. Let's do this in the parallel version. Oh, what did I do? I closed my thing. Or there we go. So I have, well, it's similar to before. I'm running on 4 ranks, example 1P, but I added these 2 new parameters. PA means partial assembly. This is how you want to run on GPUs efficiently. It's a different, you don't compute a global matrix, but you assemble its pieces only. And the important thing is this -D. -D stands for device, and we're going to use the CUDA device, which means run on the GPU. And I want to go back to the beginning of this run. And you can see here on the device configuration that it says CUDA. And there's also some information about the memory configuration. All right. So, yeah, just like that. You add -D and run on the GPUs, allows you to run faster. And then you can also use solvers, this MGX. Okay, so I knew how to give you a little bit of a background on finite elements, showing you how to run more serial examples, how to run the parallel examples, how to run with GPUs. There is much more that you can do in this example. So if you go into the beginning, you will see a number of sample runs. You can try all of this, different orders, different meshes, in serial or in parallel. And this is just example 1. Okay, we'll go into the other examples later. Okay, let me tell you a little bit about GLV's visualization tool. This is the last section here. You can either learn the keys, and if you press H, that's the most important keys. It lists all the keys. It tells you what they do. So, for example, A shows is the axis. Right? If you press it a few times, you get different options. C is the color bar, and so on. M is the mesh, and there's a mesh. There's a kind of level lines, and then no mesh. There's no direct link to the README. Oh, here we go. There's also this README at the bottom. If you click on it, it kind of it describes it in a bit more detail and tells you what the different mouse buttons do and so on. Yeah, or you can directly click. I guess we have direct links to the keys and the mouse command. All right. Alternatively, when you move in this window towards the top, these icons appear. This was the same icon we used to connect. This is another way to get the help. And there's this thing called visualization controls here. And if you click on that, you can kind of enable this some of this stuff just by clicking and pressing buttons. This is particularly useful if you're on a tablet or a phone where you do not have maybe a keyboard. Just to be clear, since this all runs in the browser, you could have the Visual Studio Code window running on your laptop and this window opening on your phone. So when you compute something on the laptop, it will just directly send the socket and make the connection and show it on the phone. And in that case, you do want to use this interface. Occasionally, depending on what you guys do, you may overload GeoVis. If you run on many MPI ranks, if that happens, you need to then come and look at this red box here. We need to kill the GeoVis server in here in the Visual Studio Code, and you will have to reconnect if that happens. All right. Oh, that's not what I meant to do. Go back to the tutorial. So this is lesson 2, finite element basics. Let me pause here and see if folks have questions. I guess we have, okay, so somebody posted about NGX. I guess we did not configure this instance with the NGX support. Apologies, we have not updated this particular, yeah, these 2 instructions will not work with this instance because the image does not have NGX. How well NGX works in general, when it can work, is another question, but it's an example of a GPU-based PMG implementation. Oh, yeah. Cool. Comes full circle. Kind of started from Hyper, so it's good to be open source again. Yeah, so sorry, do not try to build this. It will not work because of the particular image we have in this tutorial. We did get GPUs in though, and you'll see some other cool things later in this image. So we have changed it from previous tutorials. All right, let's continue. So at this point, you should have both of the environment in terms of the code and the editor and the terminal and the visualization working. You should know how to run in serial and parallel. And going back to the lessons, now you have a choice. You can look at some of the other examples, of which, as I said, there are plenty to get feeling for different PDEs, different methods. You can look at the meshing and visualization lesson, or if you're interested in solvers, preconditioners, and scalability, there is a separate dedicated lesson for that. There's no particular order. You can see some or all of them. This is estimated to be 45 minutes. This is another 45 minutes. And this is 45 minutes. So you probably can't cover all of them. So pick the one that is most interesting for you. And try to run it yourself. And let us know if you're just try to follow. For example, you go to the example lesson. We'll tell you about how the methods. It will show you how to run example 1, example 2, example 3, and example 4. The 4 prototypical examples with the spaces in the DRAM complex. And you can specify the order with -O here. Then it will then it goes into discontinuous Glerkin. Example 9 is our advection example with DG. This one has a nice video too. So let me do that. One thing you will have to do is mention here in this note, the image comes pre-built only with example 1. So if you want to run another example, you need to build it. And that's just make and the name of the example. Build example 9. Don't worry about this warning here. This just has to do some thing with the compiler that we use in this image. Okay, so now example 9 is ready to go. And if I want to do this one, so this one is a sequence of images. It's a time-dependent problem, and so I have this house that appeared here. If I click on it, as the space bar, you can see the sequence of solutions in time. A kind of cool way of looking at it is this way. And you can see we're still solving on a uniform mesh. And basically what's happening here is we're computing time steps and we're sending the solution at each time step, the visualization, and we're constantly updating the solution. I forget where, I think we're running until t equals 10. No, t equals 9. There you go. You can see that this is a digi method, so you can see some of the discontinuities here. Okay. Nonlinear elasticity, adaptive mesh refinement. I'm going to run some of this just kind of to keep something on the WebEx, but don't follow this. Just follow what is interesting to you and at your own pace. So let me run this one. This is also a video. Oh, sequence. Okay, and it told me that there's no example 15, so I had to build it. This is kind of a little too dark. Good to see. Let me make it big. You can see the ability to refine and de-refine the mesh. So adjust the element size along these rings where the solution changes rapidly, beginning at the end of the ring, and they're starting to merge. So you want high resolution close to the rings, but outside of the rings and in the interior, you want big elements. That's what's happening in this example. This example 15. Okay, so I'm going to Control-C, do it here, and let's see if that messed up my JLRIS. Okay, complex problems is another one. This one, you have to kind of change the source file a little bit, and it's described. what to do. Perfectly matched layer, PML, that's another important example for electromagnetics. The reason we need to make these changes here is that we typically visualize with multiple windows, and for this demo, we only have one example work, one window work. Okay, these are just few selected examples. 1, 2, 3, 4, 9, 10, 15, 22, and 25. There are many more. And I mentioned, if you go to mfem.org/examples, maybe you can find another one that is relevant to your work, and you can run that. G, for example, eigenproblems is another one that's interesting. Using DG, discontinuous block diffusion, symplectic integrators, and so on. There's quite a bit. So this is the examples lesson. Then the other lesson is about importing your own mesh. This is from GMesh. If you're familiar, MFEM can take input from a variety of mesh generators. GMesh is one popular open source one. You could create your own file and just drop it actually. This is basically drag and drop into the VS Code window here. And if you bring your own mesh file, you could use this instance. It will be uploaded to the instance, and you can run. So you're not limited by the files that are in MFEM. In MFEM, those files are in this data directory, and there's quite a bit of them. Some of them are 2D, some of them are 3D, some of them are surface meshes, some of them are curved. You can bring your own. This is what this lesson is about. It also shows you how to use some of the internal tools we have for meshing. Mesh Explorer, it's a mini app. So this is outside of the examples directory. We have another directory called mini apps. Well, maybe I should put dots instead of commas there. And in particular, we have a mini app called, a subdirectory called meshing mini apps. I don't know, let's make something like the toroid. There are warnings from this image, yeah. Yeah, you can safely ignore this one. Oh, right. I guess we have not tested this here. Yeah, okay, so we had an issue with the we'll have to fix in the build, in the make file, in the common directory, instead of -x linker equals, it should be -WL here. Maybe we put this in Slack. So let me see if I can build the mini app now. Imagine this is also true here. Sorry about that. Examples to work. This is for things that special mini apps that depend on this common tools that we have in some library. Most of the most time-intensive operations are on GPU. What's not the part of the code that's least important is the meshing, and in particular the adaptive mesh refinement and the data, the refinement tree. Yep. It's also not as big of a bottleneck. This -PA option that I mentioned, that is about particularly for hardware methods for a format that allows it to be much more efficient when you're targeting GPUs. Okay, so let's go back. We fixed this. Let me show you this one other meshing mini app called Shaper. What this allows you to do. Oh, come on. Okay, change this here too. 1 second. Unfortunately, can't edit and redeploy the image with the right clicks here. Okay. WL, comma, here we go. Okay, so Shaper, what Shaper does is it resolves material interfaces by MR. And it starts with a 4x4 mesh. We're going to try to resolve those on annuals. And it says continue shaping. So you answer with yes. If you do this a few times, you can kind of see basically in element I kept two materials. The materials are described by this function that is an annuals for one of the material and it's just 0 for the other. You refine them. And this allows you to ultimately get a mesh that now is, it's a type of meshing. If you want, you can start with a functional description and you can, for example, now solve example 1 where the coefficient, the diffusion coefficient has one value in the blue material and different value in the brown material. Okay. The last thing in this lesson here is about using Power BI and Visit. GeoVis is great for quick things like this and for this demo and for running it in your phone. But if you want to look at results that are massively parallel, you want to do more interesting plots or explore the data in greater detail, we support exporting to Power BI and Visit. And this tells you what you need to put in the code to do that. And that's the lesson for meshing and visualization. Okay. So the last of these three parallel lessons is about solvers and scalability. And this is about using algebraic multigrids. We have scalable MG preconditioners in all the spaces in the drum complex. The first 4 examples. There's some sample runs and adjustments, how to do that, how to test this, all of those. There's a bit about our internal multigrid solver. Then there's quite a bit about low order refined methods. This is a way to actually precondition high order discretizations. It's one of the research directions that I think MFEM is we've pioneered and we have really good support for. I mentioned briefly that we integrate with a lot of other external packages, and it's not just visualization and meshing. Probably all the packages that other numerical libraries that you've heard of, like Petsy and SuperLU and StrumPad. All of this could be enabled and built with MFEM, not in this image, but if you download it and use it yourself, and you have to connect with another simulation in one of those packages, that's something we support. All right, so these are very, very brief overview for these 3 lessons. I just wanted to touch on all of them. I'm gonna stop talking now and wait for questions, comments, anything we can do to help. Yeah, so one thing that's not, we have, I remember because we have not updated this. We don't have a lesson on BFM, but there's this effort, if you're following MFEM, you probably have heard about differentiable simulations, and we have an interface called DFM that allows you to run represent operators in a way where you can compute derivatives automatically, basically using this partially assembled approach. And this is enabled in this image. It is in mini-apps DFM, correct, Julian? Yeah. And there is a, well, I can open it here, I guess. There's a different minimal surface example, and just built like this. And you can kind of see the interface describing here what happens in the quadrature point. And which derivatives you want to take with respect to which unknowns. So this is an example that is solves a 2D minimal surface problem that I described here. But it's just a demonstration of this new interface. The point is, if you are interested in this, sorry, you could try it here. Fine. Looks like a Pringle. Okay, so depending on where you are, if you did one of the lessons, you can do another. We've done a few of them. You can continue explore on your own. This last lesson we have is kind of as pointers to all of the example codes. They're all listed here with a very brief description, and some of them are kind of suggestions for you to take a look at them with the stars. Also the mini apps. I guess we looked at Shaper, but there are many others, including some external mini apps. There's also these toys that we have that are kind of fun. They're not solving PDEs, but you can play with them. Let me see. Oh, this is not gonna work. You can try to write the simulation yourself. You could get your own mesh, put some coefficients on it, and run one of the examples and generate an image. That will be cool. We're always looking for things to add to the gallery page. So if you generate something cool, we'll consider that. The other thing you can do is you can download things and build both MFEM and GeoVis on your own machine and have them ready to use this way. If you've done building software before, maybe that's easy. If you haven't, that may take some time. We're here to help. We'll be happy to help you. And then you can dive into things like partial assembly and I mentioned this idea of storing only things that you need in a decomposed form as opposed to computing the matrix. This defined element operator decomposition. There's more details here in these pages. It's all about GPU support, the integrations. A lot of it, this should be also available in Jupyter notebooks. So let me see if this actually works. Yeah. Will it work, Justin? Oh, come on. Let me see, maybe it's this particular version. I swear, this works every time I try it, except when I demo it. Do you know why it's breaking? Let us see if we can get this one fixed. You should be basically able to just load data and have something very similar to example one. This code looks very, very similar to the C++ code. And run it inside the notebook. And then on the website, there's more. For example, if you're interested in the research part of it, there's a lot of the publication pages. We have videos. be running a seminar. If you can sign up for and look at some of the previous talks. There's quite a bit of video presentations related to MFEM here. And if you're not part of the community, you can join us on GitHub. This is where the actual code is being developed. Look at the contributing document that explains our processes. And you need first to join the organization. You need to request that. We have more than 780 people there, and they're organized in different teams, the developers, contributors, with different permissions. But once you join it, you're able to create a branch and open a pull request and all the rules there. Before we're doing this interesting and useful for you, please give us a star. That counts. All right, so the official tutorial will end in, I guess, 25 minutes, but the actual instances will not close for a few more hours. So if you need more time exploring, you can do that. And ask us questions too, but we just may not be able to respond right away. And after that, you can't just go and run request to AWS and get an instance. This will have to wait for either the next tutorial, we do this once a year usually, or download and install MFEM yourself, or use the Docker container that you can run locally. The Docker container is basically this exact same experience. Still run it in a browser. So I mean, this is one of the possible outcomes of example 9. Let me see what's exactly in the tutorial. You need to press space in the visualization window to play that video through. See, is this? There are different settings. For example, one that this looks like this around here. Sorry, for example 9. Oh, I'm in the wrong directory. No. Yeah, so it's this. If you look from above, I press space to get this video play. This is an example of a periodic mesh, and we're just basically transporting this hump. Think of it as this boundary and this boundary are identified. So all these boundaries are the same. Sunil, did you connect the visualization window to begin with this connect to socket? Did you press this and then click connect here and then press out? Okay. So this could be a case where you need to do what's described at the bottom of this page, the bottom of the finite element basics. Right. So in your terminal, I'll put it here. Okay, so first kill the server here. I will do it together with you, so I'll kill mine too. So okay, and then you have to reconnect. Then you kind of reload. And connect again. And that should clear it up. I guess Jelvis has become more robust, and I don't know where my first thinking was that the Jelvis has died. Okay, so not all mini apps and examples visualized with Jelvis. It's very easy to add such visualization, but that one seemed to be just writing to Power View. Something that maybe we can address. We have a Jelvis visual. People are complaining why certain Navia runs do not have Jelvis visuals in. This is all it takes. 5 lines of code. Hope this was a useful introduction to everyone. Just scratch the surface of what MFEM can do, which is much more. If you want to hear technical talks, advanced demos, let me mention again that the workshop is the next few days, and you can still register to attend online. And if you have any future feedback or suggestions, best way to get a hold of us is on GitHub and in the issue tracker. That's also a good place to check first before asking a question, because maybe somebody already asked it.